So thank you to the organizer to invite me and allow me to present the result that we performed over the last year, in which we investigated the possible presence of scalar field dark matter in a pair of collocated Michelson interferometers. The theoretical background in which we made this work is the one of low mass or sub-eV scalar field dark matter, in which the particle, the field is expecting to be like an oscillating classical field. In these models, these are the axion models or the axion-like particles, and the amplitude of the field is set by the local dark matter density that can be inferred by astronomical observation, while the frequency of the particle is set by its mass. This type of dark matter is assumed to be created in the early universe, and then during the galaxy formation, this dark matter field thermalized, and then it acquired a distribution of velocity, a range of velocity following Maxwell-Boltzmann-like distribution. The net result of this thermalization is that the field acquire a range of velocity, and so in the frequency we observe a Doppler shift, and so a line width. The net result is that the oscillating field has a finite coherence in space and time. We investigated the coupling to the standard model of this field at the first order. So we investigated the linear interaction of this field with standard model field. And this is parameterized in the standard model Lagrangian by the addition of a linear term. So you can see in the Lagrangian, we have phi, that is our dark matter field, f mu nu, that is the electromagnetic tensor, and lambda gamma and lambda e that parameterize the interaction of the dark matter field with the electromagnetic and electron field, respectively. The result of this linear interaction is that you expect to observe a change of the fundamental constant, like the electron rest mass or the fine structure constant. And because the dark matter field is oscillating, the variation of this fundamental constant will be oscillating as well. And this will practically result in a change of the size and the refractive index of a solid. We try to observe this dark matter effect in interferometer because you know, especially after gravitational wave detection, interferometry now can reach exquisite sensitivity, especially to differential effects. So what is the type of effect that we expect to observe in an interferometer? Interferometer, you see, is simplifying, is made by a laser, then send a beam to a beamsplitter. The beam is split in two arms, and then at the end of each arm, there is a mirror called usually end test mass that send the beam back. The two beams recombine of the beamsplitter and make interference. The interference pattern is then recorded at the output of the detector. But if a dark matter field passes through an interferometer, what we will observe, and the effect of course is vastly exaggerated, we observe something like that. So the optics of the interferometer will change in size and in refractive index. So you see that, for example, the horizontal arm, the path inside the arm will be shorter, and the beam will spend more time inside the beamsplitter that now has a different refractive index. So what we expect to observe is that the dark matter field create a differential optical path length provided by this equation, and this is what we could expect to observe in the output of a detector. The signal that we expect to see is dependent by many parameters. The main important one are the dark matter abundance, that again is set by the local density of the dark matter field. The property of the beamsplitter, its thickness and its refractive index, because it's the beamsplitter, the optics that provide most of the contribution to the expected dark matter signal. And again, the dark matter coupling parameter with the electromagnetic and the electron field, respectively. The analysis that we performed has been made using the data of the so-called holometer experiment. The holometer is hosted in Fermilab in the US. It consists of two power recycled co-located Michelson interferometer. They have a length of the arm of 40 meters, and the aim of this experiment when it has been built was to investigate the quantum theory of gravity based on the holographic principle. But what is important for our analysis is that they are co-located interferometer. So the important thing is that we can exploit in their data not the auto spectra of the interferometer, but the cross spectra. And as you can see in this picture, the cross spectra lies 5 order of magnitudes below. So this makes the holometer a perfect experiment because it's extremely sensitive to investigate this type of signal that we are looking for. Our analysis has been based using the data of the holometer acquired between 2015 and 2016. It's 700 hours of data that have been acquired at 50 megahertz of sampling frequency. And then the time series were segmented and widowed in order to compute the discrete Fourier transform. And from the discrete Fourier transform, we compute the cross spectra. What we were looking for is the presence of significant peak with respect to the background noise in the data, and we identified two possible candidates at 95% confidence level, but in the end, both of them resulted to be related to non-noise source. The first peak is at around 13 megahertz, and this is injected for diagnostic monitoring of the interferometer, and the second peak at around 20 megahertz, 20.5, is a radio frequency control sideband to lock the laser to its resonant interferometer cavities. Because we ruled out the presence of dark matter, we have been able anyway to set new upper limits at the 95% confidence level. These are our results that are now on archive that are currently under review by PRL. So you can see, for example, for the coupling with the electron field that we have been able to set new upper limits in an unconstrained region of this parameter space. And in both the coupling, we have been able to set new and better upper limits with respect to the current one. You can see there is a degradation in the high frequency part of our sensitivity, and this is due to the modulation of the signal due to the periodic frequency response of the interferometer that start to become dominant at around 3.7 megahertz. That is where the free spectral range of the interferometer lie. Just want to show your attention that there is also G600, that is the German gravitational wave detector, and about this my colleague Sander Wellmulen will talk you about tomorrow. Let me just conclude that here in Cardiff we are setting a similar experiment using a collocated interferometer. Our aim is to further investigate the quantum theory of gravities, but this will be a tabletop experiment. So the length of our arm will be around 2 meters with respect to the 40 meter of the holometer. But in the very end, we expect to have a final sensitivity of around 1 order of magnitude better with respect to the holometer. And this is a very, very preliminary projection of how our experiment can be in future sensitive to this type of dark matter signal. So you can see that when we will have our final sensitivity with, for example, 6 dB injector squeezing, we will be able to investigate this type of dark matter signal with a better sensitivity with respect to the current one, and also in a much wider range, because the holometer frequency range was up to 25 megahertz. We expect our bandwidth to be able to arrive up to 250 megahertz, so making also wider the parameter space in terms of mass of the particle that we can looking for. And that was all by my side, and thank you for your attention.